So why did we learn all this stuff? Why does it matter? We're getting to that. So, valence electrons. Valence electrons are electrons in the highest principal shell, the outermost shell. In the hotel, they are the electrons staying on the highest floor. Okay? And so we're looking at how many electrons are on the highest floor level. These electrons are important because they are the farthest out, so they're on the outside of the atom, and those are the ones that are involved in bonding and in forming ions and other chemical interactions. So we have the valence electrons, those are on the outside. In terms of the hotel, they're on the highest floor. The core electrons are all the other electrons. In the atom, they're going to be inside as opposed to being on the outside level. So this is where thinking of an atom as being a little bit like an onion. The valence electrons are in the outermost layer of skin, and the core electrons are the rest of them on the inside. So here's an electron configuration for silicon. So 1s2, 2s2, 2p6, 3s2, 3p2. The valence electrons, we identify those by looking at these large numbers here. We've got level 1, 2, 3. Level 3 is the one that has electrons in it that's the highest. 4 isn't shown because it's empty. So 3, so we're going to count all of the electrons on the third level. Doesn't matter what room they're staying in, just all of the electrons. So there's 4 valence electrons. There's 2 in the 2s and 2 in the 3s and 2 in the 3p. The rest of these electrons are the core electrons. So we got 4 valence electrons. And how many core electrons? 10. How many electrons does silicon have? 14. Any questions? Write an electron configuration for chlorine and identify the valence electrons and core electrons. Okay, so look at the periodic table. Find chlorine on there. Right? And so we're going to start at hydrogen on the first row, 1s, 2. Then we move to the second row. We come to that S block first, 2s. So we're going to fill that one up. And then we go across to 2p, and we have to go all the way across that, 2p6. And then we come around to 3s, 2. And then we keep going. We're in the 3p, and how many spaces over in that p block is chlorine? 5 spaces. Electron configuration from the periodic table. Identify the valence electrons and the core electrons. Well, what's the highest occupied level? 3. So all of the electrons on that third level, the third floor of the hotel, are valence electrons. So there are 7 valence electrons. And then the core electrons are everything else. There's 10 core electrons. Questions? It turns out, excepting helium, of course, because it's got to be ornery, that elements in the same group, the same column in the periodic table, have the same number of valence electrons. So hydrogen, lithium, sodium are all in group 1a. They have 1 valence electron. We just did chlorine. Chlorine's in group 7a. It has 7 valence electrons. Neon and argon are in group 8a. They have 8 valence electrons. Helium can't have 8 valence electrons because he only has 2 electrons. but he does have a full valence shell. It's hard to think of helium as being feminine because it's a he, right? Carbon, how many valence electrons? 4. The group number tells us how many valence electrons there are. So the number of valence electrons for any main group element is equal to the group number. And the row number is equal to the highest principal shell. So if we look at, say, sulfur. Sulfur has 6 valence electrons, and they're in the 1, 2, 3, the third level. So this chart, we ignored these things underneath before. These are showing us the highest levels for the different elements. So from argon to potassium, potassium would be argon plus 4s1. Calcium would be argon plus 4s2. So 4 is the highest level, and it's got 2 electrons in there. It's in group 2. It's got 2 valence electrons. We can look at bismuth. Bismuth has 5 valence electrons. It's in group 5. All of these have S2P3, and this is level 2, 3, 4, 5, 6. It all ends up being basically a grid. And what's so crazy to me, again, is that the shape of the periodic table was established before we even knew what electrons were. And then we learn more about the electrons and we find out that they fit in the shape perfectly. It's not a coincidence. It's because the number of valence electrons affects those properties that Mendeleev used to order things and set up the periodic table. So the transition series, the transition metals, that represents filling of core electrons, core orbitals, and the number of valence electrons there is mostly constant. There are a couple of discrepancies in there, and we're not going to worry about them. The principal quantum number of the d orbital is 1 less than the row number. So if we look in here, here's scandium. So the 4s has filled, and then we go down to the 3d. Is that 3d electron a valence electron? No, because 4 is the highest level. All the valence electrons are on level 4. Yes, it's higher in energy. It came in last, but it's not a valence electron. In the hotel, you're looking at the highest floor, 4th floor, that has anybody staying on it. How many people? Doesn't matter what's going on underneath. Okay? So this has 2 valence electrons, 2 valence electrons, 2 valence electrons. It goes across that way for most of the time. There's a little weirdness here with chromium and copper. They do some sketchy things, but it's a weird Groupon deal. So all of these generally have 2 valence electrons. We're also going to see that the number of valence electrons has to do with the charges that those elements take as ions. And since all of these have roughly the same number of valence electrons, then it's more difficult to predict what they're going to do. But the main group elements are very predictable. I really should rearrange this and put this up earlier. So this is example of how to write the electron configuration for phosphorus from the periodic table. So you find phosphorus, and if you're going to do the noble gas configuration, you're going to go up and to the end to find the previous noble gas. Oops. So we've got neon, and then after neon, we're going to go through these blocks. So this is the 3rd level, S. 3s2, and we jump across here because we have to stay in the same row, and 3p, 1, 2, 3. Again, you can use the lecture videos as guided practice. Stop at the beginning before I start explaining how to do it and see if you can do it yourself, right? And then go ahead and see if you're on the right track. If you do that a couple of times and it's still not making sense, please text me. So written out instructions represent the inner configuration with the symbol for the previous noble gas. It has to be the one immediately previous. The outer electrons are found by the element's position in a particular block of the periodic table. The highest quantum number is equal to the row, the period number, and the principal quantum number of the outermost d electrons is the row number minus 1. Like I said, it looks to me like the middle section of the periodic table sank down. That it should be up higher, and that's where 3D is, but it sank down. That's not what happened, but it helps me remember. Let's do tin. First of all, what's the element symbol for tin? Fn. So we got to find tin. There he is. Okay, there's tin. So it does not say regular or noble gas. So let's do the noble gas shorthand because it's easier. So what's the noble gas immediately before tin? Krypton. So it's going to be krypton. I need some space, so I'll do it up here. Krypton, and then we look at what comes after krypton. So this is 5, right? 5s2. So there's 5s2, and then we have to go through here. That's sunk, that's 4d, going all the way across is 10. And then we get over here. This is back to 5p, and we went 2 spaces in, 5p2. Okay?